Guys, today we are going to start a new topic, and that is circular motion. So, by looking at the name circular motion, you can easily understand that circular motion means when something revolves around the circumference of a circle. Okay. Sometime when you see something like this also, like something is moving like this with some curvature, so you can consider this whole motion as a combination of lots of circular motion. For this portion, you can see it's a part of a circle. For this one, you can say that it is also a part of a bigger circle. For this one, you can say this is also a part of some kind of curvature. So in that case also, we can think that this is nothing but the what you say a combination of circular or this kind of motion. Now we will be talking about only the very basic of circular motion, that is when you have a circle like this and something will be revolving around it. Okay, so we will be telling this as circular motion. Now basically this is a kind of uniform circular motion. Uniform because it's a simple circle and the distance of that object which is around revolving, like if you are that object. Or let's say it's better, we can say that we have a stone at the end of one thread. Okay, so the stone, and I am just revolving the stone like this. So if the stone is moving like this, you can see that the distance from me to that stone is always fixed. That means the r is always fixed and the stone is revolving in the circle. So basically this whole thing is happening in two-dimensional plane, right? Because like when something is moving, you can always assign some x coordinate and some y coordinate to that stone, because this whole thing is happening in a single plane, right? Now the thing is that when you will be having a circular motion like that, let us draw this once again. Okay, let us draw this circle, and here we can see that either I can, so this is the center. Okay, so either I can say that at this point, when the body will be at this point, the position will be x comma y. I can say that. Even also I can say that this position I can define like this also, key this position I can define like that. This is the r, and this is making an angle theta with my horizontal axis. So this is my horizontal axis, say, and this is my vertical axis. So I can always say that if this is my horizontal axis, then this point P, okay, at this point P, the position of this point can also be given as r comma theta. Why r comma theta? Because if you defined r and if you define theta, then also you can locate that object. So either you can do it by using x and y, or you can do it by using r and theta coordinate. Okay, so this thing is called your Cartesian coordinate, and this thing is called your polar coordinate. So these two are the coordinate systems, and both of them are used to locate any object in two-dimensional plane. Now when you have a circular symmetry, that means like this circle, because if you rotate the circle around you, it will be circle only, right? So there is a symmetry. Now when you have a circular symmetry, you can always use the polar coordinate to locate any object, because if my origin point is O, and if you just say that the object is at, let's say, uh, 2 comma pi by 3, so you will immediately understand that maybe this 2 is in meter. So you will immediately understand that from my point O I have to go to, so I have, my radius will be 2, and then I have to move pi by 3 angle from the horizontal to get the point. So in this way also you can easily what you say, define that or the locate that point. Now why we are talking about this, because now we are talking about circular motion, so it will be very much important for us to locate any object or any point in like the circle, in the circumference of a circle in which it is revolving. Now what we can do here, so one more thing is must, that I think you have remembered that I have talked about differentiations. So differentiation will be needed here. Why I will be telling you. Okay. So let us first define what you say, the like position of this like particle. So we can always write r as a vector, because see, r is having a direction from O to P. So r can be represented as a vector whose magnitude is r. So the magnitude of this vector is r. So what we can do, this r vector simply is enough to represent the what you say, position of this particle P, and theta is can be taken to define the direction of the particle P. So in that case, what we can do, we can take the component of r in x-axis, so that I can understand how much of this r position vector is responsible for the horizontal shift. So I can easily see that if this direction is I cap, because I have told you x direction basically is taken as I cap, and y direction is basically taken as j cap. So what I can do here, I can take out two components of r. So I, instead of writing r, I can write r as the combination of the portion along x-axis, that is your, for this triangle OP and let's say M. So for OPM you can use your trigonometry, and you can easily write that OM is the contribution of r along x-axis, and that is your r cos theta. Now I am not giving the what you say, mod sign, because again and again I have to write it. So whenever I am not giving any vector sign, think that it is the value only. And along j axis I can always write this as r sine theta, right? So this is what we can do when we take the origin at O point. Okay, so we can express r using these things. Okay, now what we are basically going to do in the next page, we are going to shift our origin. So let's say this is our what you say, revolution orbit, and here is the point P. Now instead of taking the origin at O, we will be taking the origin at the point where the particle is. So what we are going to do, we are going to take the axis here. So this will be my x-axis, and this will be my y-axis. So this is my x-axis, that is the I cap direction is along this way, and this is my y-axis, that means the j cap direction is along this way. Now I know that the direction of my r vector is along this way, so the direction is this way, right? But the value, I know that this much is the value, let it be, but the direction is along this way. So basically what we do here, we talk about like if we take r, so I can always write r as like this, what I told you, that if this is my theta, I can write r as r cos theta, r vector as r cos theta plus r sin theta, right? Okay, now we know that the velocity is always regarded as the distance covered by time, but we know that velocity is also a vector quantity, and in this way the velocity will be dr by dt. Why differentiation? Because when we are trying to find the rate of change of some quantity, now that means I am going to find that in unit time what will be the change of r vector. You can see in this circle that in every moment the curvature is changing. So as the curvature is changing, so that means I have to take a very small quantity, that means I have to take a very small portion of r so that I can get an instantaneous value. Okay, because if I don't take a small portion, like say I am taking this big portion, so you can see that in this big portion already there is a lot of curvature, so this is not a straight line, and this formula is basically I can use for straight line only. So that means what we have to do, that means you know that velocity v equal to s by t, distance by time, this is a equation of a straight line, but this whole thing is a curvature, so you cannot approximate this whole curvature as a straight line. So what you have to do here is you have to differentiate the function. Why differentiation? Because in my one of the video I have told you all that differentiation is a tool that slices the function. So if I am doing slicing the function itself, I can see that if I take a very small portion like this, I can see it will be approximately looking like a straight line. And also we have seen that if we differentiate the circular equation, we will be getting a linear equation, that is the equation of a straight line, and then we can use that formula v equal to s by t. So that means we have to do differentiation here, and if we do differentiate this term, see r is a constant term, right? So r is not varying with time. So as r is not varying with time and it is a constant, so it will come out. Now differentiation is having some some property like this. If a is a constant, so it will come out, and because this term, that is t, is dependent on t, so that will be dt like that. So whatever is the constant can come out. Okay, now here you can see that if I take out r, so I will be having only dt cos theta. Now you can say how then theta is dependent on time. So you can easily see this thing, that as the time is going, this point p, like the particle which was at p will come to another place, let's say at q, after some time. So that means this theta will also change, because whatever is the theta at my P point will not be theta at Q point, because in Q point you can see the horizontal distance will be this and R will be along this, so the angle theta prime will always be changed, right? So we can say that yes, theta is a function of t time. And also in the next case, what we will do, we will write so d dt of sine theta. Now I cannot differentiate till the time I don't express theta as a function of time. That means I have to write theta in the expression of time. Now here is the thing, when you have something like this moving and your theta is changing with time, I can always write that theta is proportional to time, right? So because if time is increasing, theta is increasing accordingly, right? So I can always write theta is equal to some proportionality constant, so we will write that as omega and time. Okay, because see, I told you here also when that particle from P point is coming to Q point, always my theta is increasing, so I can say that theta is proportional to time, and that's why theta is equal to omega t. I can write omega is a proportionality constant. This omega is called angular velocity. Why this is angular velocity? Because you can write from here that my omega is equal to theta by time. From here I can write this. That means how much theta is being covered in how much time. So per unit time, whatever is the theta covered is my angular velocity. And what is linear velocity? The distance covered in unit time. So you see here there is a two different thing in classical mechanics. One is your linear portion, that is for your linear distance that you can measure with scale like that. And one is the angular distance and angular velocity. That means when something will be revolving around a circle or something like that. So once I know that my theta is equal to omega t, so I can rewrite this equation. Okay, so if I rewrite the equation in the next page, you can see here that my v, that is dr dt, is r ddt of cos omega t, because instead of theta I am writing omega t, plus r ddt of sine omega t, right? Now this v, so this v is a vector, and here one thing I have missed, that is the I cap and the j cap, because this term is the vector, and so this must contain the directional term as well. So what we are going to do here, we are going to write the I cap and j cap as well. So I cap and j cap was there from before, so here we will have I cap and j cap. Okay, because this is not only the value but also the direction as well. So now what will happen, see, when you have d dt of whatever d theta of cos theta, you will be having minus sin theta, and d theta of sin theta is your cos theta. Okay, now if you have something like this, let's say you are having, instead of this you are having d dt of cos alpha theta and d dt of sine alpha theta. Alpha is a constant. So in that case, what will happen to the alpha? Alpha will come in front. There will be minus, obviously, and this will be sine alpha theta. And this one will be alpha will come in front from there, and this will be cos alpha theta. Okay, so that means the the constant part, which does not depend on the differentiation factor, that is theta in this case, always come out, and cos becomes sine, and when cos becomes sine there is a minus sign in front of it, and when sine becomes cos there is no minus sign. And this thing, the proof how these things has come, you will learn in math definitely. So we can use this knowledge of differentiation here, and what we can write here key r. So my omega is a constant because omega does not depend on t, because I have already assumed that this is a uniform circular motion. So omega is constant as we have assumed a uniform circular motion. Now this motion is not a motion when you switch on the fan, because in that case your the speed increases slowly, right? So this is not that motion. But even if omega is not constant, we can then also find the value. Okay, so at first we will do with this assumption, that is the simpler one, and then we will go into that. Okay, because that will be also quite interesting. Okay, so basically if we now do, so you can write that this is minus, omega will come in front, this will be sine omega t, and then we have plus r omega, and we have cos omega t. There will be I cap and there will be j cap. So you can see that the velocity is having two different components. One is along I cap and one is along j cap, right? And now if we find out the acceleration, because we know also that acceleration is my dv by dt, that is the change of velocity with respect to time. So here again we have to differentiate it. So my r omega is constant, so I can write it outside with minus, and we can write d dt of sine omega t I cap plus r omega d dt of cos omega t j cap. So now I can do the differentiation again. So again my omega will come in front, so this will become r omega square. My sine will become cos, so this is cos omega t I cap, and then from here also omega will come in front, but cos theta ka differentiation is minus sine theta, so there will be another minus sign, r omega square, and we will be having sine omega t j cap. So one thing you can see, if I take common minus r omega square, I will be having cos omega t I cap plus sine omega t j cap. And if you recall this term, that is your cos omega t I and plus sine omega t j, this is nothing but your r vector. So you can always write this as your, instead of your r vector you can write it. But one thing you can see here, that there is r here, right? But there is no r, only cos omega t I cap and sin omega t j cap. Now from here we can see one thing, that if I take r common, so I will be having cos theta I cap plus sin theta j cap, right? And I know that any vector can be represented as the value of that vector and the direction of that vector. So if r is representing the value of that vector, so this term cos theta I cap plus sin theta j cap representing r cap, that is the direction of that vector, right? So instead of this thing, what I can write minus r omega square r cap. So what is this r cap? R cap is merely the direction of this a acceleration vector, and you can see that in my next page, what I will be doing, I will be writing this acceleration term again. So we have gotten that this is r omega square r cap. Now coming to our realization, let's say this is my circular motion, and this is my center, the body is revolving somehow. So the direction of my acceleration is important here. So you can see that the direction of acceleration is always in the negative, that is the opposite side of r. So if this is my direction of r, so this one is the direction of r cap vector, right? So the direction of my acceleration will be towards the origin, that is if something is moving like this or like this, so like clockwise or like anti-clockwise, in the both of the case, because there is no sense if you see, if something is rotating in clockwise and you are seeing from upside, but if you move your eye in downside, you will see that it is rotating anti-clockwise. So this clockwise or anti-clockwise is a perspective thing, right? So you are not in front of me, so I cannot tell you practically, but you can imagine that if something is moving, like your fan is moving in any direction, let's say when you are downside and you are looking at the fan, you can see that the fan is rotating in anti-clockwise sense. But if you can move up, it's better with stand fan or stable fan, you can see that whatever is the sense you are looking, if you change the side, if you go in the back side of that fan, the sense will be changed. Now in that way, so whatever direction it is rotating, the direction of r cap, that is the increase, in which direction r is increasing. So obviously r is increasing from O to P, so more you go from O towards P, the value of r will increase. But the value of your acceleration, because acceleration is also vector, so it will be having some value and some of the direction. Now the direction is minus n r cap, right? So in that case you can say that a cap, the direction of acceleration of that particle due to this circular motion, is towards O always. So wherever is the particle, let's say the particle is here, that is at Q point, so then also the acceleration will be towards O. So you can say that the acceleration always in circular motion acts at the center, towards the center. Okay, and the value of this acceleration is r omega square. Okay, now you must be thinking, array, what is this omega has come from? Omega was that proportionality constant. Now look one thing, we can easily make a relationship with our known value, that is velocity, with omega. So if this is my circle and the particle is revolving in the circle. This is the center. So let's say the particle was at this point P, and after some time the particle has moved to this point Q. Okay, so the particle has come from P to Q. Now you can see one thing, when the particle was at P, the direction of the velocity was this way. That means the direction of that particle, like while going, was this way. So the direction of velocity at point P is this way. The direction of velocity at point Q is this way. So you can see that in each of the points in that circumference of the circle, the direction of velocity is always changing. Maybe the value is same, but the direction is always changing. So V vector is not a very good thing here to describe the motion, as the direction of this thing is changing. So V vector itself will change, because V vector is consist of value and the direction. So as the direction is changing, so obviously the V vector itself will change. So this is a not very good thing to take under consideration, so that we can understand the motion of a circular thing. But what we can do, actually, basically what we can do, we can create a relationship between V and our omega. Now we see one thing, my omega is theta by t, right? Or you can say, for small change in theta and for small change in time, omega is equal to d theta by dt. Actually, basically d theta is a very small quantity representing, and dt representing a very small time quantity. Okay, that is a very small duration of time, as small as you can think. Okay, more smaller than that. So let's say it has covered theta angle, and r is the radius. So you know the arc length, that is the length from P to Q, that is your arc length, is your r theta, that you know already from your trigonometry, that the arc length always is a multiplication of the angle between your final and initial and final position, and r is the distance between them. If you multiply them, you will get the arc length. Now we know that PQ is r theta, so I can say that my velocity is what? Actual or speed, let's say speed, I'm talking about only the value, not the direction, only the value vector. I know that the speed, if I say this word speed, that means there is no direction added to it. So if I talk about the speed, I know that speed is the PQ by time, right? Now PQ is my r theta. So what I can say, that this r is independent of time, because this r will be same in all of this position, wherever the particle is in around the circle, r will be same. So theta by t I can write as omega. So you can see here a very nice relationship, and that is very important for us to do numericals and all. A relationship between my angular change and my actual distance change. So I have linked one thing, that is the actual linear velocity, the speed, linear speed, and the angular speed. That means how much the angle is changing with respect to time, with this relation, v is equal to r omega. Now if we use this v equal to r omega here, so we can get one more thing from this. So we can write r omega square as r omega into omega. So I can always write this as not without doing this. What I can do here, I can find omega from here, that is my omega is v by r. So if I put here instead of omega v by r, so that will be v square by r square, and ultimately I will get from here v square by r. So the acceleration is v square by r. So this acceleration is which acceleration? This is the acceleration for circular motion. So this is not that linear acceleration I am talking about. Okay, linear acceleration means if like you switch on the fan and you see that the last point of the fan is like speeding up. Okay, so when it is speeding up, then that will be a like there will be some linear acceleration as well and some angular acceleration as well, but this acceleration is something which is called your centripetal acceleration. And how to what is the centripetal acceleration? An acceleration which acts always in the origin, like towards the origin point. Okay, that means when you tie one stone, okay, with a thread and then you try to rotate the stone with that thread, you will feel something that the stone is one stone wants to go far apart. Okay, like outward direction, so you will have a force towards outward direction, and if you rotate it very harshly, the stone will go away, okay, in the outward direction. By just so my thread will not be there, so obviously it will tear off the thread and then it will go away in the outward direction. But why the stone is bound to that circular motion? See, obviously if something is bound in the circular motion, that means this object, somebody has to always bend his path, right? That means this object at P wants to go in this direction, so I have to bend its path. So in the next motion I have bended a little bit, in this motion again I have bended, this motion again I have bended. So in all of the point something is there which is bending the motion, that is which is changing the direction of the motion, and that is what the centripetal acceleration is doing. So centripetal acceleration is acting so that the object is bound in the circular path. Okay, so this acceleration and the linear acceleration is a different thing. We are not talking today about linear acceleration. In the next day we can talk about linear acceleration, and like the real situation when we turn on the ceiling fan switch and we see that it is speeding up also. But in this case we are not talking about speeding up, in this case we are talking about only the circular uniform motion where the angular speed is same. That means omega is constant, and you have seen here that we have during our differentiation we have taken omega as constant and we have taken it out of the differentiation, that's why. So this is the simpler approach. Okay, and we have gotten that the centripetal acceleration is the acceleration which is responsible to bind the particle which is revolving in a circular path. So that it can rotate in a circular path, this acceleration is working hard. Okay, and this acceleration is always inward. Now you will say, sir, then why we feel that the stone wants to go away, that means outward, why we feel that? So that we will study in the next chapter, okay, when we will be talking about forces, that why you feel that it wants to go outside. That is you are feeling, right? But what stone is feeling, right now when it is moving in a circular path, that we are talking about in this chapter. The stone is feeling that something is binding me, okay, so that I can bend my motion each and every time, like each and every point, and I just rotate about this single point O. So two relations are very important for today, that is your V equal to R omega and your A equal to R omega square. These two, if you remember, then most of the math in this chapter we can do easily. And one more thing, what is omega? So I will just make a gist of it. So first we have seen that omega is theta by t, that is delta theta by delta t, or you can say d theta by dt. So this we will use for our analysis, but this we will use for our numericals, practical life. So this is important for practical uses, like to directly do the maths. And one more thing, that is V equal to R omega, that also I have seen. And acceleration is, so I'm writing the vector one only, acceleration is R omega square R cap, or we can write R omega square A cap, where A cap, the direction of acceleration, is opposite of that of the R cap. Okay, so these three things we have learned. In the next class we will be talking about frequency and the situation where speed can, like there will be linear acceleration as well. Okay, so for today this much is the class. Please do ask me, because this is little bit different what you have learned. So please do ask me, because there are a lot of differentiation. Okay, so okay, bye and see you in my next class.